Our next speaker will be Karen Meech from the University of Hawai'i, and Karen will talk about chemical fingerprints of the early solar system and its dynamical evolution.
Okay, thank you very much. I'm going to switch gears a little bit now. So I'm more interested in looking at the dynamics of how we form the solar system from the perspective of astrobiology, giving us a solar system that can support life. And as we know, some of the key ingredients for habitability and life include water, energy, as well as suitable temperatures. And right now we're not at the stage where we can explore that by just looking astronomically at other solar systems. As you saw in the previous talk, we have beautiful images from ALMA that give us a hint of the process of planets being born with these dark lanes where we may have a giant planet forming, but the scales are wrong. We really want to look in close in the habitable zone where you could have liquid water, say on a terrestrial planet. And that may be the focus that we can get with the next generation of arrays. This is the very large, the ALMA array in the deserts of Chile. The next generation that might be available in the 2030s will have the ability to look in closer to the habitable zone, both looking at the formation by imaging as well as getting at the chemistry. And a lot of this is really important because as of today, we have maybe potentially 13,000 planets that have been discovered in over 4,000 planetary systems. And right now we know of maybe 30 to 70 potentially habitable planets. So what we really want to look at is how you get the ingredients for life to the inner solar system. Now, one question is, we've got one example of an inhabited solar system where we have a terrestrial planet in the habitable zone, and that's us. But the question is, are we a unique solar system from the assembly point of view? And if you look at some of these typical diagrams where they plot period versus mass, and you look at where our solar system planets are located, it does look unusual, although some of this is selection effects. We can't yet see close-in terrestrial planets. But it is an interesting question to ask. Is there something about the dynamical makeup of our solar system that was unusual? So we've got one example of an inhabited solar system, and the way to go back and look at the process of forming our solar system now is, of course, to look at the remnants of that process. And for this talk, I'm focusing on the small bodies that have preserved some of the chemistry and some of the physical stages of that process, namely the comets, asteroids, which may have preserved volatiles, and of course, this includes some meteorites. Now, forming a solar system is a very complicated process. These are some nice figures from Ilse Cleves, which illustrate some of these steps. You have a collapsing cloud of gas and dust. And within this collapsing cloud, it collapses faster near the center of the solar system. You have the young protostar warming up. You're going to have temperature gradients both radially and vertically. You're going to have mixing in the disk. You're going to have a rich chemistry on the hot surface, a warm molecular layer where you're going to get chemistry going, and then a cold midplane. As material infalls, some of the ices can sublimate and then refreeze near the midplane at very low temperatures. At the same time, you also have the dust grains, which are inheriting some of the chemistry of the ices. They start to coagulate and form the planetesimals, which, as some of them get bigger and bigger, they start to interact with Jupiter and the giant planets. And then there's movement within the disk. So we've got the chemical signature set by the temperature, and then the dynamics scrambles up that signal. So when we're talking about what does life need on a planet, we mentioned that you need the organic compounds, other ingredients, you need a source of energy, and a liquid solvent, water. If we take a look at the inner solar system, it's largely very dry. We do appear to have a lot of water on the Earth, but it's actually not very much by mass. So the inner solar system is quite dry, and one question is, if we're talking about habitability, how much water do you actually need? Some of the leading theories for origin of life suggest that it must happen on dry land because you need some cycles of wet and dry. For example, you have a lot of raw material falling in from space, And this needs to somehow get together. The idea is that it falls onto the surface in warm ponds, and some of this aggregates the material. You get lipid layers forming. It dries out. This concentrates the material. Through many, many cycles of wet and dry, you eventually encapsulate the ingredients that become life. So these are some ideas about how life starts. You also can't have too much water on a world. If you have a world with life that eventually has 5 oceans worth of water, you're going to shut off some of the cycling some recycling of materials. You will lock up some of the ingredients that life needs, so it will no longer be recycled and available for biology. And then some say if you get way too much water, a water world, then you've got a high pressure ice layer between the rock and the upper layers, and this also inhibits life processes. So clearly we need just the right amount of water. So where does this come from in our solar system? A good starting place is to look at the timeline for the formation of the solar system. We've seen that we've got very good estimates of when it started from the meteorites. We also have seen this from the returned stardust samples. We also know from the other end that we had vast amounts of water very early, by about 4.3 billion years. And this comes from both samples of zircons, very ancient crystals. A lot of these are found in Australia, which showed that these volcanic eruptions erupted in large bodies of water, and they were quenched very rapidly. And when you look at the dates, they're all around 4.3, 4.4 billion years. We also have granites that some of the oldest granites from the Canadian Shield require multiple cycles of volcanic eruption in water. So we know we had water very early. So where could it have come from? The Earth and the inner planets formed inside the so-called ice line, where in the solar nebula the gradients were such that it's too warm in the inner region for water to exist in the ice form, but it could exist in the gas form. And Mike Drake was one of the proponents of saying, early Earth could have just captured its water because the gas got stuck onto the grains accumulated eventually into planetesimals and built the Earth. Others say some could have come this way, but once you start to get high velocity collisions, you're not going to keep the water. And this would have happened very early. Some of our Japanese colleagues suggest that maybe it came a little bit later, after the Earth was largely formed. If you had periods of magma ocean, and we know there were maybe one or more periods when the whole surface was molten, if you had at this time a hydrogen-rich atmosphere, you could chemically manufacture water on the surface of the Earth. This would have had to have happened very early, within the first 10 million years or so. But we don't know if there was ever a period where we did have a hydrogen atmosphere which overlapped a magma ocean. And then, of course, third, things that were forming planetesimals outside the ice line could have easily been injected inwards, intersecting Earth and delivering some of the water. But the question is, how do we tell these different scenarios apart? So we need to look at some signatures. And the idea of how to trace these processes came in the 1980s. For a long time, people had known that Earth's isotopic signature in deuterium in the ocean water was anomalously high compared to what was expected from the protosolar nebula based on measurements of the interstellar medium. And so they were puzzling over this, and then with the European mission to Comet Halley, the Giotto mission in 1986, they actually made a measurement of the D to H in water and found that it was elevated. The Earth oceans are about 6 times higher than the protosolar nebula. Comets, at least Comet Halley, this is actually a nice ground-based image of Halley from 1986, was about a factor of 2 high. And this led people to suggest that, well, maybe it really was the outer solar system material that brought the water in. However, a few more comets were measured in the 1990s, and 2 really bright comets showed that they were the same as Halley. And people started to say, well, comets can't be the only thing delivering water because the D to H is too high. We also had the meteorites that had measurements of D to H, and they had a wide range of values, including those that matched Earth oceans. So looking in a little bit more detail at how well do we really know this whole scenario, let's take a look at what we know about the D to H of the solar system. As I mentioned, it was initially estimated based on measurements from the interstellar medium. People knew that processes in space, chemical processes, can increase the fraction of deuterated species hugely at very low temperatures. They developed chemical reaction networks with thousands of chemical reactions and found that at low temperatures you get extreme deuteration. But that doesn't tell us a clue about what's going to happen to the solar system until you start to get more sophisticated models where they start to see the layered structures and they can do the chemical modeling to see what you predict in terms of not only the chemical species, but the isotopes. So here's a model from Karen Meech from the early 2000s showing distance from the sun in the protosolar nebula versus height above the midplane, and the different colors show the amount of deuterium that was predicted in the disk. And what you can see from this is that there isn't a single D to H ratio in the disk. It's a complicated function of distance, and what is not shown on here is it changes with time. So absent any measurements of looking at gradients in D to H in other solar systems, what I think we can really say from this is we don't really know what the initial solar system D to H was in the context of us trying to unscramble the history of the solar system. In terms of comets, after the measurement with Giotto, the comet measurements were done astronomically using facilities. Hale-Bopp and Hyakutake were measured at infrared wavelengths from Mauna Kea. That was for the deuterated species. For water itself, it was measured in the ultraviolet at a different time. And of course, comets can be highly variable, so these were low signal to noise measurements. But once more and more sophisticated equipment, including high-resolution spectrometers on Keck, were available, they could start to make this measurement on fainter comets. And so a whole slew of measurements were made showing that the brightest comets, which all happened to be long-period comets, were much higher than Earth's oceans. Finally, with the Spitzer Space Telescope, one Jupiter family comet, which was expected to have formed colder in the disk, farther from the sun, should have had a very high D to H. It was measured near Earth-ocean water. So people threw up their hands and said, clearly we don't understand the models of disk chemistry because it's backwards. So they devised some new models. Yang in 2013 had a new model which now predicted lower D to H in the outer solar system. The scientists thought it was solved, excited for the measurement from Rosetta, and it was the highest D to H that had ever been seen. So people threw up their hands and said, we don't know what the comet contribution was. They're all over the place. Of course, what we do know is that these comets didn't contribute to Earth because they still exist. So we don't really know what the comets are saying. In terms of the meteorites, if you look at the D to H in the meteorite collection, you can see whether we're talking about various types of meteorites or interplanetary dust particles. They really do line up very well with Earth in terms of the D to H. But as you saw from the previous talk, the meteorites don't tell the same story when you look at all of the compounds they can contribute. So while they might match in D to H, they aren't a good fit for Earth itself in terms of the collection that we have. So let's take a look at the other side of this equation, the Earth's measurement of D to H. This was done from Earth-ocean water, the largest access we have to water on Earth. And it occurred to some scientists that maybe we aren't measuring the right water. Mike Model at the University of Hawai'i put together a review paper to look at how much water do we actually have on Earth. And most scientists can agree on how much water is on the surface, various estimates of Earth ocean volume, lakes, rivers, streams, atmosphere. But as you go deeper and deeper into the Earth, you can only go so far where you make measurements into the crust. Once you're getting down into the upper mantle, you can use laboratory experiments to get down to about 700 kilometers to assess how much water there could be. Beyond that, it's seismic data. But the bottom line is, we don't have a good clue how much water we have in or on Earth to within an order of magnitude. Mike Model himself feels it's about 3 ocean masses of water on Earth. But that led us to think about, well, if most of the water is inside, maybe we're measuring the wrong water for this story. And so after a meeting in Iceland, where a typical field trip afterwards, you go see some sites, we went to a geothermal site where the scientists said, it's okay, you can go over, it's not poisonous, this is just water, it's cool, it's primordial water that comes out of the earth. And of course, the little light bulb goes on. I thought, how exciting. Went and talked to some geologists at the University of Iceland. They said, well, she's dead wrong, it was water, but it's rainwater that comes down, gets heated up, and comes out as steam. So I was disappointed, and he said, but we do have signals of primordial gas coming out of the earth, and these are from hotspots like Hawaii, Iceland, where you have material coming up from the core mantle boundary, and we know it's primitive from the helium isotopes. I said, has anyone ever measured the D to H? And he said, no, very hard experiment. You'd need a new ion microprobe, which UH had just gotten. So we ended up getting some field samples to go out and collect rocks. And one of the postdocs at Hawaii looked at some of the melt inclusions to get some ideas, both from samples from Iceland and Greenland, what the D to H of Earth's water on the interior was. And she found out that it's much lower than Earth-ocean water. So in fact, on this one, we have to put a question mark there. So now what? We seem to have made a mess of our story of really trying to understand where we're coming from this one isotope, D to H. Well, it turns out there's a lot of systems one could explore to try and trace what's happening in the early solar system. So we talked about D to H. This is a cartoon showing the chemistry and the dynamical mixing component. The cosmochemists for years were trying to understand the oxygen isotope signatures in meteorites. And they came up with the idea of oxygen self-shielding, that a large amount of the oxygen is locked up in CO in the disk. It's photodissociated by ultraviolet radiation. The most abundant isotope, oxygen-16, it's 99.97% of the isotopes. So this very quickly becomes optically thick, and there's no more UV at the right wavelength to break it apart. Once these are broken apart, oxygen combines with hydrogen, and you eventually make water. Once it's optically thick for oxygen-16, we start seeing predominance of oxygen-17 and 18 that can give us the range of distribution we see in the protoplanetary disk. So that's a different process, a different physical process that can trace what is going on in the disk. We have the nitrogen story, which was alluded to a little bit previously in the question and answers, where we see differences across different bodies. This could also be a self-shielding component. It could be in a low-temperature ion molecule reaction, such as we have with D to H. And then there's also the noble gases, which, when you are condensing some of the gas during the early solar system, if it condenses at very low temperatures, below 100 Kelvin, it can trap a lot of other gas molecules, and it traps them at very large amount differences depending on the temperature at which it condenses. So this can give you another indicator of where things formed in the disk. So where do we go from this? Well, and thank you, Francois, I don't have to explain this in gory detail. As you heard, we have the NCCC dichotomy, and this gave people an idea about we have two different reservoirs that may have been due to an infall of late R-process material. What some of the authors recently have proposed is that, again, Jupiter opened up a gap early. The material that would normally be flowing inwards, the tiny little grains, will get stopped at this pressure bump and remain out here growing planetesimals, whereas in the inner disk, we're still growing planetesimals. They can't mix until Jupiter's core gets to about 50 Earth masses, at which point now it starts to gravitationally scatter planetesimals so that they can get across this gap. And so one idea is that Earth either got its water from just the gas in the inner disk, Earth formed inside the ice line, wherever that was, and then later it could have been delivered by Jupiter scattering material inwards. Now, if Jupiter scattered material inwards, it would have hit everything in the inner disk. It would have gotten to Mars, Earth, Venus, Mercury. It would have also gotten captured in the asteroid belt where it could remain today. Some of the problem with looking at comets as the deliverers is that we don't know exactly where they formed, except they formed outside the ice line somewhere. That could be anywhere in the disk. And the ones we see today clearly didn't contribute to Earth. The beauty of this is whatever got tossed over could still be stored in the asteroid belt, available for study. So what we really needed to unravel some of the isotope story is to have something in a place today that was delivered dynamically. And I think a key discovery in the 1990s, and has been really studied since then, has been the discovery of icy bodies in the asteroid belt. These are the main belt comets. Henry Shea and Dave Jewett have done a lot of work on this. These are dynamically in the asteroid belt, and many of these have activity. They have little tails that look like ice-driven activity that reoccurs every time it comes close to the sun, and these have volatiles. It wasn't known that they had volatiles until recently, when finally JWST imaged, got a spectrum and found water coming out from these objects. So in fact, if you have something close by that we can study, this is an exciting potential for looking at the isotopes. However, these things are so faint, you can't do them remotely. This would require an in situ flight investigation, either exploring them in situ or better, bringing samples back. The in situ exploration could get at the isotopes with a mass spectrometer, but if you want to go after the refractory components, which are key to understanding the inner solar system and the organics, you're going to have to bring a sample back. Well, what about the dynamics? Now, we've been talking about the chemistry and trying to unravel that. Well, in 2013, a comet was discovered by the Pan-STARRS telescope. Richard Wainscoat came into my office and said, hey, we've got a long period comet. It hardly has any tail, and it's close to perihelion. Is that interesting? I said, oh yeah. Normally they should look like this. This is a little runt. We decided to call them Manx comets. Not an official term, but for the tailless cat, because I didn't want to keep saying long period comet with hardly any tail. That's a mouthful. What was exciting at first was this vast cloud of comets orbiting the sun at about 50,000 AU, the Oort cloud. Jan Oort, when he inferred the existence, he was just plotting orbital properties, the semi-major axis of the orbit versus the number of comets. He said this spike here, which is the Oort cloud, is too narrow, because as comets come in the first time, many of them will come close to the giant planets, their orbits will be perturbed, and they should fill in this region. They're not there. So he proposed that maybe they lost their ices and we just didn't see them again. So the excitement was this could be maybe Oort's lost comets. We got a spectrum of this. These are the colored points, and this is in comparison to asteroid spectra. And it was a real surprise. This had an S-type inner solar system rocky type spectrum, yet it had a little wisp of a tail. So what's going on here? One thought is that maybe, yes, it's starting. Maybe this is something that formed near the snow line. It formed at a temperature where it could get the minerals of the S-type. Then it got kicked out. It accreted some ices. It got sent out to the Oort cloud, just like any of the planetesimals that get out there, and we don't have to watch all 4 billion years. Eventually, it gets perturbed inwards by a passing star, and we see it coming in on a long period comet orbit. The reason this is exciting is if you take, there's been decades of work on dynamical simulations of the solar system, where this is from a recent paper by Carter, where what we're looking at is distance from the sun, and the bluer planetesimals are icy, coming from the outer solar system. The orange and yellow are from the inner solar system. What we're seeing here is you can either have planets, giant planets, migrating inwards, or they can form in situ and not do much migration. And what this will tell us is the fraction of this rocky material that could get kicked out to the Oort cloud. So the idea is if we can start looking at these Manx or nearly inactive objects and look at their surface reflectivity, their colors, we might get a clue as to which of these scenarios is more correct. Or, as we're starting to see, this diagram here shows color versus, this is a spectral reflectance, so we've removed the sun. Most comets are just red. The Manxes seem to be all over the place. We have one so far that has this rocky intersolar system signal. The way nature works, it's probably both. We probably have things near the ice line, and we're probably seeing some of Oort's dead comets. Well, what next? The floodgates are opening. Right now, we're discovering a lot of these interesting small bodies from existing surveys, but the Rubin telescope is just about ready for its first light in early 2025, and by probably late 2025, early 26, is going to be starting its 10-year survey. The expectations are that we will get about 100 new MBCs. We will get maybe 10,000 comets where we will have rich coverage over their whole orbits. We're going to have maybe 30,000 TNOs, lots of new asteroids, and perhaps even 10 interstellar objects. So we're going to have a lot of sample that we can look at for potential investigation of the isotopes and what went on in the early solar system. So on my last slide, I just want to talk briefly about the value of the sample return. I think in order to untangle the scenario of the dynamics and what was going on in the early solar system, you need a lot of isotopes. You can't just use one system, and that was the point of the example with water. You need to, because you need so many, your best bet is to return the material to Earth so that you can get both the volatiles and refractory if you can. And ideally, you want this for a lot of objects. So I'm advocating to get samples from MBCs, Manxes, LPCs, Jupiter Trojans, and then of course get out to the KBOs. And if you want to study other solar systems, also from interstellar objects. I don't know what's harder, interstellar objects or a Venus sample return, but I'm advocating for all small bodies in the solar system. And I think this is going to help us understand the processes that lead to the formation of the solar system and, in the context, habitable zones and habitable planets elsewhere. All right, thank you.